When most people picture a snake strike, they imagine a quick blur, something so fast that the human eye can barely register it before it's over. For decades, scientists studying venomous snakes have relied on observation, dissected specimens, and behavioral patterns to understand how a strike works. But now, slow-motion technology is rewriting what we thought we knew. A new study released this week by a multinational research team has captured the most detailed high-speed footage of snake bites ever recorded, revealing astonishing mechanics behind the attack behaviors of both venomous and non-venomous snakes. What they discovered not only challenges old assumptions but could help improve medical treatments, antivenom development, and public safety. Their conclusion is simple but profound. Snake strikes are more complex, more precise, and more diverse than humanity ever realized. A breakthrough in animal motion science. The study was carried out by researchers from the University of Queensland, Kyoto University, and the National Geographic Exploration Lab. Using 8,000 frame-per-second ultra-high-speed cameras, scientists recorded over 300 strikes from 47 snake species. This included well-known venomous snakes such as rattlesnakes, vipers, cobras, and taipans, as well as several non-venomous constrictors like boas and pythons. Dr. Lena Marshall, the lead herpetologist behind the project, explained during a press briefing. A snake bite is one of the fastest movements in the animal kingdom. We knew they were quick, but until we saw the footage slowed down, we had no idea how much detail we were missing. According to Marshall, the technology allowed them to observe subtle muscle contractions, fang deployment, and micro-adjustments in a snake's jaw and head position that occur in fractions of a millisecond. The hidden precision of venom delivery. One of the most surprising discoveries was the unusually high precision with which venomous snakes inject venom into their targets. Popular belief suggests that snakes simply strike, deliver venom, and retreat. But slow-motion footage shows that the process is far more calculated. 1. Micro-alignment before impact. Even at lightning speeds, snakes make fine adjustments to target specific areas of the victim's body, often preferring soft tissue zones. 2. Fang curvature optimization. In just 0.01 seconds, many species rotate their fangs slightly to maximize penetration depth and ensure venom delivery efficiency. 3. Pressure-controlled venom injection. Contrary to the old assumption that venom simply flows into the wound, the new footage has shown that snakes actively regulate venom pressure with specialized muscle contractions. Dr. Hiroshi Tanaka from Kyoto University described this process. It looks like a hydraulic system in motion. The venom glands and muscular structure work together with incredible coordination. The snake doesn't just bite, it controls the venom flow based on the resistance it feels. This discovery might help pharmaceutical researchers develop more accurate artificial venom delivery systems for studying toxin effects without needing live snakes. How fast is a snake bite? Much faster than expected. Scientists have long estimated that many snake species strike at speeds between 2.0 and 3.5 meters per second. But slow-motion footage revealed another surprising truth. Several species can strike even faster, some exceeding 4 meters per second. The black mamba, often considered the world's fastest striker, reached a recorded speed of 4.5 meters per second in the experiment. But even more astonishing were a few viper species that achieved similar burst speeds. Dr. Marshall noted, what shocked us wasn't just the speed, but how controlled the motion was. Even at maximum velocity, their precision remained incredible. The discovery may also explain why snake bites in the wild happen so quickly that victims rarely react in time, even when they believe they are prepared. A better look at dry bites. Another breakthrough came when researchers analyzed dry bites, strikes where snakes bite but do not release venom. Previously thought to be random or accidental, the footage suggests a different story. Dry bites are often intentional. The footage revealed that snakes can activate a very subtle muscle motion before the strike to close venom ducts if they do not intend to inject venom. This supports theories that venom is a valuable resource and snakes use it strategically. Environmental biologist Drive. Andrea Ruiz explained. Greater than, a snake wants to conserve venom for hunting. When they perceive a threat that doesn't require a full envenomation, they sometimes deliver a warning bite instead. This finding could change how medical professionals evaluate the likelihood of venom delivery in certain species. New insights into snake evolution and adaptation. Some of the most intriguing footage involved comparing venomous and non-venomous snake species. Scientists discovered key evolutionary traits. 1. Constrictors have slower but more forceful bites. Boas and pythons delivered slower strikes, but their bites were accompanied by extremely strong jaw pressure, ideal for grabbing prey before tightening coils. 2. Venomous snakes have evolved rapid, hit and release, strategies. This minimizes risk by reducing the amount of time they are exposed to retaliation from prey. 3. Some species show hybrid strike behaviors. A few rear-fanged snakes displayed a mix of piercing strikes and persistent biting, showing a transitional evolutionary strategy. These findings help explain how diverse snake families developed unique hunting methods across millions of years. Micro-behavior hidden in the blur. Before slow-motion analysis, many micro-movements of a snake's strike went unnoticed. Scientists now know that snakes briefly tense their entire spine like a coiled spring before launching forward. Rotate their skulls slightly to allow fangs the best angle of entry. Adjust their trajectory mid-motion using minute neck flexes. Retract fangs with a fast snapping motion to avoid self-injury. One of the most remarkable discoveries involved facial muscle activation, which researchers had not documented before. Slow-motion footage showed that snakes exhibit small facial twitches milliseconds before striking, perhaps signaling an internal trigger mechanism. Marshall compared it to greater than a sprinter's foot tightening on the starting block right before launch. Unexpected defensive behaviors revealed. In addition to offensive strikes, the footage captured new insights into defensive bites. 1. Defensive strikes are often faster. Many species deliver quicker strikes when scared than when hunting. 2. Defensive strikes show reduced accuracy. When afraid, snakes prioritize speed over precision. The goal is simply to create space, not necessarily to inject venom. 3. Retreat is built into the motion. A defensive strike often includes a built-in recoil motion, pulling back before full contact, that minimizes body exposure. This helps explain why many defensive bites to humans are shallow or glancing rather than deep, targeted punctures. What this means for antivenom research. Perhaps the biggest practical consequence of the study is its potential impact on antivenom production. Current antivenom research focuses mostly on venom composition, but the new footage shows that venom quantity, depth of injection, pressure of injection, fang angle, tissue type targeted, all vary widely from species to species. Future antivenom development may need to factor in strike mechanics rather than treating venom injection as a uniform action. Dr. Tanaka emphasized, greater than, antivenom research has always focused on what venom is. Now we need to study how venom enters the body. That is where this footage becomes invaluable. Implications for wildlife conservation. The researchers hope the footage will also improve public understanding of snakes, many of which are endangered. Snakes often have a negative image due to fear and myths, but the new visual data shows them not as mindless aggressors, but as highly evolved, calculated hunters that strike only when necessary. Conservationist group SnakeSafe International plans to use the footage in educational programs to reduce human-snake conflict in rural areas. Program Director Liam Jeffers stated, greater than, people fear what they cannot see or understand. Slow-motion footage uncovers the beauty and precision of a snake's strike. It helps build respect rather than fear. Improving safety training for hikers, farmers, and first responders. Understanding strike range, trajectory, and timing can significantly improve safety training. Based on the footage, researchers developed new guidelines. 1. Safe distance should be increased. Many snakes can strike up to half their body length, sometimes more if highly coiled. 2. Many strikes occur diagonally, not straight forward. Training materials will be adjusted to account for unexpected strike angles. 3. Reaction time is irrelevant. Since strikes occur in under 50 milliseconds, humans cannot physically dodge them, removing the myth that quick reflexes can prevent bites. 4. Boot and glove designs could improve. The footage showed common penetration points that protective gear manufacturers can redesign. Slow motion cameras capture rare behaviors never seen before. Beyond strikes, researchers recorded surprising behaviors that shocked even seasoned snake experts. Checkmark snakes aborting strikes mid-air. Some species stopped their attack mid-motion after detecting unexpected movement. Checkmark venom spray adjustment. Cobra species altered their venom spit angle in real time based on target height. Checkmark pre-strike vibration signals. Some snakes vibrated tail tips or body segments milliseconds before striking. Checkmark double strike sequences. Certain species performed 2 rapid strikes in less than 0.2 seconds. These discoveries challenge long-held assumptions about snake behavior complexity. A new era for herpetology. The research team believes that this is only the beginning. Advances in slow-motion technology, paired with 3D motion capture and eye-assisted frame analysis, could transform our understanding of animal biomechanics. Dr. Marshall summed it up. For years, snake strikes have been a black box, too fast, too blurry, too misunderstood. Now we can finally see the truth, frame by frame. And what we're seeing is extraordinary. The study's findings will be published in the upcoming issue of Nature Ecology and Evolution, with full video footage expected to be uploaded to public databases. A final look, what slow motion has taught us. After analyzing hundreds of strikes, scientists have reshaped the modern understanding of snake behavior. Slow motion footage has revealed snake strikes are precise, calculated movements. Venom delivery is actively controlled, not passive. Defensive and offensive strikes differ dramatically. Evolution has produced diverse and specialized strike mechanisms. Antivenom research must consider strike mechanics. Public education can reduce unnecessary fear and conflict. Human eyes may never be fast enough to see a snake bite as it happens, but thanks to modern technology, we can finally understand what has been hidden in the blur for thousands of years. And with that understanding comes new respect, and perhaps a safer future, for both snakes and the humans who live alongside them.